Hello, now we're starting the chapter on just more detail about making a graph of a function based off of the information you can get. The overall module title is Limits at Infinity and Asymptotes, but we're going to learn a lot. There's a lot of detail with this one, so I'm just going to brace yourself and get involved. There are 3 pretty good lessons here. So let's get started with that. First one is limits at infinity. That's what we're doing right now. So calculate the limit of a function as x increases or decreases without bound, and recognize a horizontal asymptote on the graph of a function. And so, a lot of this, you probably have those skills already developed from your pre-calculus days. And I feel like some of this is a refresher, but let's go ahead and go forward. So let's talk about informal definition. The values of f become arbitrarily close to L as x becomes sufficiently large. We say the function f has a limit at infinity, and we write the limit as x approaches infinity of f of x equals L. If the values of f of x become arbitrarily close to L, that is, so we're approaching a value in both these cases as for x greater than 0. As the absolute value of x becomes sufficiently large, we say the function f has a limit at negative infinity, and we write limit as x approaches negative infinity of f of x equals L. Basically what we're doing in this, we're approaching this asymptote L, and so we're approaching y equals some value, like y equals 5, for example. So here's a definition. If the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L, we say that the line y equals L is a horizontal asymptote. So that's what it's really talking about. It's just horizontal asymptotes. We saw this back when we did our pre-calculus days. We're graphing different types of polynomials. This could extend beyond polynomials. So in a case like this, where it's a trig function over x, and we're going to see one that has a sine function, but as you go on, this keeps oscillating above and below, but it's always approaching this line. Okay, so let's do some examples. For each of the following functions f, evaluate the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. Determine the horizontal asymptotes for f. So we have 3 parts. There's an A, B, and a C. So for our first part, we have the limit. Just put this over. Oh, look, I'm using green instead of blue. I like to use blue. So we have the limit as x approaches infinity of 5 minus 2 over x squared. That's the limit as x approaches infinity of 5 minus 2 times, check this out now, the limit as x approaches infinity for 1 over x times the limit as x approaches infinity for 1 over x. Okay? So what's this going to give us? It's going to give us 5 minus 2 times, and the limit as x approaches infinity for 1 over x is 0. So we can multiply that by 0 twice there, and we just get 5. So the limit as x approaches infinity of f of x equals 5. But likewise, because that's going to be, it's still zeros, the limit as x approaches negative infinity, so that'd be still 1 over negative infinity, 1 over negative infinity, that's of f of x, that'll still be just 5. That's our asymptote. Y equals 5. Let's look at B. So for B, we have the limit as we're looking, well, let me do this, build this up a little bit first. First, we know that -1 is less than or equal to sine of x less than or equal to 1. We know that. And we've divided everything by x. Then we have -1 over x is less than or equal to sine of x over x less than or equal to 1 over x. So if we look at the limit as x approaches infinity of -1 over x, that's going to be 0. And the limit as x approaches infinity, negative infinity of, or sorry, we're still doing positive infinity, of positive 1 over x, the one on the right side, that's also 0. So the limit as x approaches infinity of sine of x over x is going to then be 0, kind of like the squeeze theorem there. So likewise, the limit as x approaches negative infinity of sine of x over x also equals 0, because each of those boundaries are going to be going towards 0. Okay, let's look at our C now. C says f of x equals tangent inverse of x. So this one takes a little bit of thinking first of all. So think about this. We know what a tangent graph looks like. So if we were to graph this and at negative pi over 2 to pi over 2, it looks something like this. I didn't draw that very well. Comes up, crosses at 0, 0, and goes up. And the next one does the same type of thing. I mean, so we know graphically, as it approaches pi over 2 from the left, what it's doing, and from the right, what it's doing. Now, this problem is actually talking about the inverse function. So we can say the limit as x approaches pi over 2 from the left side, what we're seeing here on this left side over here, of tangent x, that's going to become infinity. So we can then consider what's happening with the reciprocal function. Therefore, the limit as x approaches infinity of tangent inverse of x would be pi over 2. Because we see as it approaches pi over 2, it's the original function. So what was the domain becomes the range. What was the range becomes the domain. Okay, now let's think about this. The limit as x approaches pi over 2 from the right side, so this side over here, of tangent of x is going to be negative infinity. So we can look at the limit as x approaches negative infinity of the inverse function, tangent inverse of x. That's going to be negative pi over 2. So y equals pi over 2 and y equals negative pi over 2 are horizontal asymptotes. So I should have been citing from this side over here. That's our negative pi over 2, are horizontal asymptotes. Okay, let's go on. Another one here. Evaluate the limit as x approaches negative infinity of 3 plus 4 over x, and the limit as x approaches infinity of 3 plus 4 over x. Determine the horizontal asymptotes. So we would look at the limit as x approaches negative infinity of 3 plus 4 over x is going to be 3 plus 4 times the limit as x approaches negative infinity of 1 over x, which is 3 plus 4 times 0, which is 3. And the limit as x approaches positive infinity of 3 plus 4 over x is going to be 3 plus 4 times the limit, as x approaches infinity of 1 over x. So it's 3 plus 4 times, again, 0, so it's a 3. So our horizontal asymptote is going to be y equals 3. Okay, let's try another one. This one didn't print out. I don't know what's going on there, printing for this section. So the question that came up, hang on. This one was just a true and false. And it says every ratio of polynomials has at least one horizontal asymptote. And the answer is false, because if you remember from your pre-calculus days, if the power of the numerator is greater than the power of the denominator, then you have an oblique or slant asymptote. It could be a quadratic asymptote. It could be lots of things, but it wouldn't be a horizontal asymptote. So the answer is false here. Next one. Definition. We say a function f has an infinite limit at infinity and right limit as x approaches infinity of f of x equals infinity. If x becomes arbitrarily large for x sufficiently large, f of x is large, okay. We say a function has a negative infinite limit at infinity and right the limit as x approaches infinity of f of x equals negative infinity if f of x is less than 0 and absolute value of f of x becomes arbitrarily large for x sufficiently large. Similar, we can define infinite limits as x approaches negative infinity. So definition, here's the formal definition. We say f, so this kind of goes back to the epsilon delta stuff we did before, but instead of being having a limit to a point, now it's a limit at infinity. We say f, a function f has a limit at infinity if there exists a real number L such that for all epsilon greater than 0 there exists n greater than 0 such that the absolute value of f of x minus L is less than epsilon. For all x greater than n, in that case we write the limit as x approaches infinity of f of x equals L. We say a function f has a limit at negative infinity if there exists a real number L such that for all epsilon greater than 0 there exists n less than 0 such that absolute value of f of x minus L is less than epsilon. For all x less than n, in that case we write the limit as x approaches negative infinity of f of x equals L. So what we're looking at is if we're bigger than a certain point and we're a certain value of n of x, but we're getting super closer and closer and closer, arbitrarily closer to a specific value, then it's going to be, that's the limit of that function. So let's see how to write this up when it comes to doing these problems in this format. Okay, so we have the limit as x approaches infinity of 2 plus 1 over x equals 2. So think of it as we had f of x minus L. We have the absolute value of f of x minus L. In this case, that's going to be absolute value of 2x plus 1 over x minus, not 2x, just 2. Minus 2, which is going to be the absolute value of 1 over x. And so then that's going to have to be less than 1 over n, which is epsilon, I should say, like 1 over n this way. So let me back up a little bit here. We get to choose the values. So I mean, this kind of builds up with let epsilon be greater than 0 and let n equal something we choose. So if we look at 2 plus 1 over x minus 2 equals that absolute value of 1 over x as we saw, this value needs to be less than epsilon, so that x would be then greater than 1 over epsilon. Now, this is our side work here. So maybe I'll go back and erase this part right here. If we let n equal that 1 over epsilon, this is what it becomes then. That you can say, therefore, for all x greater than n, this is one of those key points in the definition. Then we can build it back up again. 2 plus 1 over x minus 2 is equal to the absolute value of 1 over x, which is then less than 1 over n. And let me stress this here. If x is bigger than n, then 1 over x is less than n. So think about this. 100 is more than 50. 1 over 100 is less than 1 over 50. And then, so 1 over x is less than 1 over n, which becomes our 1 over epsilon, which is epsilon. And that's the path we're trying to follow with this. So let me kind of put it all on the screen if I can. So again, this is side work off to the side here. Let epsilon be greater than 0. Let n equal something that we come up with, and we came up with it down here. And that was that 1 over epsilon. Therefore, for all x greater than n, this is my f of x minus the L equals that 1 over x is less than 1 over n, which equals 1 over epsilon, because n is 1 over epsilon, which is our epsilon. That's it. Okay. I know this is kind of weird, and it seems even more weird than what we did before with the epsilon delta stuff, but this is it. And don't worry, this is not going to be a big focus of the course here. I just was showing how this works. So we're going to do the same thing with this one. And we have our format is this. Let epsilon be greater than 0. Let n equals something. We're going to choose that to be something. So what's that something? Well, let's do the side work over here. We are looking at that absolute value of 3 minus 1 over x squared minus the 3 is equal to negative 1 over x squared, the absolute value of that. And being an absolute value, the negative goes away, so it's 1 over x squared. It needs to be less than epsilon, which means our x squared is greater than epsilon, because if you flip it, sign changes. And so that x is greater than 1 over the square root of epsilon. And that's what we're going to choose to go in here, is 1 over the square root of epsilon. Now we build out the formalities. We have the absolute value of 3 minus 1 over x squared minus 3 equals 1 over x squared, because the absolute value, which is less than 1 over n squared, which is epsilon. And therefore, the limit as x approaches infinity of 3 minus 1 over x squared equals 3. Okay. Let's do another one. I have another definition here. Formal definition, we say a function f has an infinite limit at infinity and right limit as x approaches infinity of f of x equals infinity. If for all m greater than infinity, there exists an n greater than infinity such that f of x is greater than m. For all x greater than n, we say then, so here we have the limit being infinity, or negative infinity. We say a function has a negative infinite limit at infinity and right limit as x approaches infinity of f of x equals negative infinity. If for all m greater than 0, or less than 0, there exists an n greater than 0, such that f of x is less than m for all x greater than n. So this is the case where we have the limit at infinity and limit being infinity and limit being negative infinity. Okay, so we have a formal process for this now. So you use the formal definition of an infinite limit at infinity to prove the limit as x approaches infinity of x cubed equals infinity. Okay, so our format, our process goes like this. Let m be greater than 0. We're going to choose, this over a little bit, n equals something. What's that something? Well, let's figure it out. So consider here f of x is greater than, now let me back up a little further. We are talking about this x cubed must be greater than this m value, so that x must be greater than the cube root of m. And that's all we really need to do here is this is going to be that cube root of m. So now we write over here the consider f of x is greater than the cube root of m, or that x is greater than the cube root of m. That means that x cubed is greater than the cube root of m quantity cubed, or that x cubed is greater than m. So we'd say that our f of x is greater than m. So I think we need to not have this part here. We just get rid of that part there. So consider x is greater than the cube root of m, because the x is greater than the n, and n is equal to the cube root of m. Then we cube both sides, and we come up with, this is our f of x, and then now we have f of x greater than m. We can then conclude that the limit as x approaches infinity of x cubed equals infinity. And that's it. Okay, let's see here. We have a couple more examples to go. And it says use the formal definition of the infinite limit at infinity to prove that the limit as x approaches infinity of 3x squared equals infinity. So again, we're going to be doing that side work over here. And the side work would be that this f of x is 3x squared. We'd set that, make that greater than m. And then we can divide by 3, so x squared is greater than m over 3. And x is greater than, I should say, the square root of m over 3. Okay? So now we write up the way they want it written. Let m be greater than 0. Hey, we already, we have that's referenced. And then we let n be equal to what we just came up with, the square root of m over 3. And then consider that x is greater than n, so greater than the square root of m over 3. So that x squared is greater than the square root of m over 3 squared. So x squared is greater than this m over 3. So if I said it wrong, it's the square root of m over 3 squared. That gets rid of the square root. Then we multiply both sides by 3. 3 times x squared is greater than 3 times m over 3. So these cancel. Not thrilled with the way that inequality looks. Still looks bad, but okay. So this 3 times x squared, that's my f of x, is greater than m. Therefore, the limit as x approaches infinity of 3x squared equals infinity. To me, kind of a common sense thing, but okay. We have one last problem here. And again, didn't print, so it wants us to evaluate. I'll write it up here. Evaluate the limit as x goes to infinity of 7x plus 5 over 10x squared minus 11x plus 5. Now, there are several ways to do this, and if you recall from your pre-calculus days, if the power in the denominator, is more than the power in the numerator, then our limit is just going to be infinity. So the degree in the numerator is 1. Degree of denominator is 2. So our limit, so we should know by that the limit's going to be 0. Now there's a longer way to do this, and I just want to expose you to that as well. That if we take the limit as x approaches infinity of 7x plus 5 over 10x squared minus 11x plus 5, and we multiply this by, see this, x squared is the biggest power, so 1 over x squared over 1 over x squared, we would have the limit as x approaches infinity of 7x over x squared minus or plus 5 over x squared, all divided by 10x squared over x squared minus 11x over x squared plus 5 over x squared. And that's going to give us the limit as x approaches infinity of 7 divided by x plus 5 over x squared over 10 minus 11 over x plus 5 over x squared. And then that limit, then, you end up with 7 over infinity is 0. 5 over infinity is squared is 0. Over 10 minus 11 over infinity is 0. Plus 5 over infinity squared is 0. So 0 over 10 is 0. And that does it for this section.